Facebook page. There's quite a bit of posts of saying, hey, this movie is related to science. Hey, this is, I mean, you do. You say, this is the interesting stuff. Why do we study physics? Because we're interested in it. And I think that's really important. Karina has served as a student assistant at the observatory and as the student assistant at What Physicists Do. When Karina came to me with this project, I'm going to give context, which is, we were talking about measuring two stars and then that one blocking out the light of the other star, and with Henry's project, it's two stars like our sun. And Karina said, you know, you've been talking in classes about this wonderful thing where we can find planets going around other stars. And that is a very difficult job indeed. And Karina said, I'd like to try to see if we can measure a transit, which she'll discuss, a way of measuring a planet going around another star. And this is a kind of monumental task, and it reminds me of another student who came to me with a monumental task. And I think we'll be very pleased with the results. Let's give a warm welcome to Karina Smith.
Imaging Translating Exoplanets by me, Advisor Scott Severson. That's me at the telescope for these measurements. Anyways, the goal was to measure the change in measured brightness during the event of a transit. And we used various programs such as the Exoplanet.eu is a database of exoplanets, the Newtonian telescope with CCD instrumentation, which we took the images with. We used Google Sheets to do calculations, the US Naval Observatory Julian date converter because some calculations were done using Julian dates. And we used this one astronomical imaging textbook, and we used astronomy imaging software. What is an exoplanet? Some people do not know this because these weren't even confirmed until the 90s, but it's a planet that goes around a star that is not the sun. And I like this particular image, even though it's actually a bit outdated now, we have far more, because this was from a few years back, and most exoplanets were discovered using the Doppler method, which, like the transit method, which I'll discuss, was biased towards planets that were larger and closer to their stars, known as hot Jupiters, and that's why there's so many big ones. What is a transit? It is when a planet goes in front of its star and we see a dip in the light curve. And usually it's only done with exoplanets, not planets around our own star, because there's only two in front of it. There were actually two transits of Venus in the last few years, but we're not going to see this for another 200 years. Method for selecting an exoplanet, or the exoplanet and the star. Now this was actually a very important part because we needed something that would be visible in the northern hemisphere that was experiencing a transit within the next few months, and actually specifically before our observatory went down, because some of you know that happened recently. And that would be visible at night during, where we are, because we can only take these measurements at night. And so we got a list of things that may have counted, and then using Google Sheets, we did some calculations to find the dates and times that these would happen. And then we had to do some conversions as well, because it was all in Julian dates, and eventually we found our target. And this is how we did it. The different things we have to mind. Okay, and the star is HAT P13, and the exoplanet was HAT P13b. And some things about HAT P13 is that it's very similar to our sun. It's a G4 spectral type star. It's 10.62 V apparent magnitude. It's only slightly bigger than our sun. It's larger, it has larger radius, more mass, but it's not by that much. And it's about 214 parsecs away. It's in the constellation Ursa Major. It's not one of the big stars that we notice in Ursa Major, but it is in that region, and that's where it is. And it has at least two confirmed planets, actually. One is HAT P13b, the other is HAT P13c, which is further away and takes longer, so we wouldn't have used that. And there may even be another one, but that has not been confirmed yet. And HAT P13b, the planet in question, it is the second and largest closest planet discovered orbiting HAT P13, because remember we said that there might be more, but this is the only one of the only two confirmed. It was discovered using the transit method in 2009, and it's a hot Jupiter that is, well, here it is compared to Jupiter. It's It actually has less mass, but it's larger because it's a hot Jupiter, so it gets kind of puffy. And it has an about 3-day orbital period, so it's pretty close. That's a pretty fast orbit. And getting the images, we did this at the Sonoma State Observatory using the Newtonian telescope and its CCD imaging technology. And this isn't one that you just look through. It takes pictures with a special camera. And over the course of several hours, we took them at different color wavelengths, in blue and infrared and visual, and at different time exposures so that we could get different information, because we needed to put everything together to get what we want. And what happened there?
It's on 2 slides, so just talk about each picture.
Okay. This is the telescope that we used. That I was just talking about. This picture was taken during the day, a few hours before we started taking the images. There is the camera that I mentioned, and this is the Sonoma State Observatory. As you can see, the roof is not on, that's why we can see the trees and everything. Or this was the Sonoma State Observatory, I should say. We're going to have a new one soon. But it's not going to be that different. It's still going to have that. And this is at night, and me actually taking those images using this 90s computer. And there's the images being taken. See, this is measuring the time exposure, and this is all red light because that gets it's less interfering than blue, which unfortunately is the only color that the keyboard comes in, but yeah. And okay, the imaging process, much more important and exciting. So we used IRAF technology, that's a program, and the first part we had to do is put all those images together so we have all the information we need, and we have to clean it up a bit, get rid of all the noise because there was some weather change, there was some movement of various stars over time, and then so that involved, mostly getting rid of the dark, because the dark is also, you have to get rid of that too, not just light. And then the next more important, well, no, it's just as important. Actually getting the information, we had to measure the brightness that changed over the course of the night. And, oops. So there is an initial image. There's our star right there. As you can see, it's not very even. It's more dark over here, it's bright over here, and it's really noisy. But here's a nice one, and the star is right there. And there's some lines right here that's the result of things getting moved and cleaned up. And so some ways that we get the information that we got was first, well, I'll explain that actually later, using this. This will make it more clear. So here is an example. This is a different star, but this is an example of how it works. So here's your star. Here's the sky. And this is the area between the star and the sky. And you can't just divide out or subtract out, other stars. You also have to get rid of, the brightness of the sky in order to get just the brightness of your target. So that's what aperture photometry involves. And okay, and here's an initial graph. As you can see, it's not very nice. It's noisy, and it goes down, it basically halves over time, and you only really notice anything interesting right here. However, here it's been made all nice, and we've gotten rid of the brightness of other stars in the sky, and it's still noisier than we would like, but there's an actual pattern. This is the expected transit, and this is what we got. And so basically, our findings is there was a noticeable change over time, and we assume that it wasn't as perfect as it could have been due to things like the change of weather conditions, which caused reddening of other stars as they went through more atmosphere, or appeared to rather. So as we're dividing out that brightness, it was changing in ways that it shouldn't have, hence this sinusoid right here. And also because we just, this isn't like some in space telescope, it's just on the land. But however, we still got some pretty good information, and we proved that we can in fact get these kinds of measurements from Sonoma State. And this is the first time we've gotten a planetary transit. As you know, we got a star transit before using our technology, and that's good. And a little bonus slide for you. Dr. Severson really liked what we found, and he decided, you know, because he pretty much figured out all the issues, but we didn't have that much time to work on it further, but he decided that he would work with it a bit and see if he was right about what the issues may have been, and this is what it would look like. And oh no, if it was made by a professional initially, and as you can see, that's really nice, and I could have done that too if I had more time, but I didn't. So this is a bonus slide. And special thanks to Dr. Severson and the spring 2017 Astronomy 331 class, because they were actually there the night that I did this, because I took these images literally the last night that the observatory was available, and they were also having our class, so they got to witness this happening. And also here's some image sources, because I used some images that were not my own, and you want to know where those come from, and that's my presentation